Merlijn, you're muted.
Hello, everyone. How's the transmission? Can everybody hear me?
Excellent.
That's wonderful. Welcome to the third instance of Meyer Sound webinars. Today, we're going to talk about Downtilt Translation in MapXT. And for those that attended previous webinars, by now, you probably will know that as a warm-up exercise, I will go through the Zoom platform that we're using for this webinar, just to make sure that everybody is familiar with the Zoom platform and can ask questions during the course of this webinar. So I'm going to share my screen.
2 settings there would help. And let's take that down by 3 or 4 dB. Let's do a tight.
Okay, there we go. So Downtilt Translation will be today's topic. We're using the Zoom platform, and everyone is expected to see a window in front of them, not unlike the one that you see here. In the bottom left corner, there is the option to unmute your microphone if you desire to do so. Next to it is the button that allows you to turn on your camera. Furthermore, there is the possibility to see your fellow attendees by clicking on the participants button. And if you do that, a window opens to the right side. And it also offers the option on the right-hand side to raise your hand, which is a very cool feature because this way I know that you want to ask a question. It's not going to be a monologue as far as I'm concerned. It's going to be a dialogue. And that allows us to channel the questions. If you raise your hand, then I will try to pay attention to that. Be mindful, I'm all alone, whereas there is 200 of you at this point. So please forgive me if I cannot address all your questions on the spot. That being said, there's also the option to chat. If you click on the balloon, then the window on the right side splits in half, and there is a chat window in the bottom of the right-hand side window where you can address the nation by typing a message, which goes to everyone. Or if you see a familiar person, a fellow colleague, family member, then you can also send messages to any of the participants on the call. So if you want to ask a question, don't refrain from asking questions. Please raise your hand, and I'll make sure that I'll try to address those questions to the best of my ability. Okay, so Downtilt Translation. What is it all about? Well, let's see. What are you going to learn during this seminar? During this seminar, you are going to learn the following things. During this seminar, you will learn how to run multiple instances of MapXT at once, which you can do. We will learn how to work in multiple dimensions. We will learn about Downtilt Translation, which is, after all, the reason for this webinar. And finally, we will learn how to determine the usable width for Leo family products, such as Leo, Lion, Leopard, and Lena. A recording of this webinar will be uploaded to our YouTube channel upon completion of the webinar. So we're about to use Map. Map can be downloaded for free at the Meyer Sound website at meyersound.com/product/mapxt. And today we're going to look at a venue, simple venue, straightforward venue that I've modeled in SketchUp just to spark your imagination. It's a simple stage. It's a rising audience plane, and the audience lives at air height, which today will be 1.2 meters. However, if I want to understand how to design a system that covers this area properly, then I need to think in more than one dimension. I need to think in 3 dimensions, which means that in a map ecosystem, I'd like to work with at least 2 instances of map. Typically, we need a plan view that allows us to observe the listening plane and the stage and the loudspeakers from above, but a section view to show how I am shooting the loudspeakers, how I am displaying my array, also comes into play. And sometimes you even need a transaction view, depending on what it is that you are trying to do. So how can we make it possible to run multiple instances of map so that we can work in multiple dimensions at once? For those that run map on Apple macOS, it's a very straightforward process. You go to the folder where your map application lives, you right-click the application, and you choose duplicate. If you choose duplicate, then a copy of your application will show up in that same folder, and all that's left to do is give it an appropriate name so that you can distinguish one instance of map from another instance of map. In my workflow that has been recommended by Meyer, I typically work with 4 instances of map. There is the so-called plan view, there is the section view, there's the transaction view, and occasionally I might actually have need to also look at a balcony. Windows users have it slightly easier. Windows users can launch multiple instances of map at once. So by clicking the shortcut, double-clicking the shortcut, you can open multiple instances in a Windows environment. For Apple users, this is the way to do it. And that means that I will be using today 2 instances of map, one for plan view and one for section view, which gives me enough dimensions to look at today's model. So on the right-hand side, we have a 3-dimensional view of today's model. And notice that I can do a plan view and I can do a section view. And I've prepared my map files accordingly. So let me overlay the map files that I've prepared so that you know what it is that we're looking at. So I have a map file for plan view and I have a map file for section view running simultaneously. In the preparation of these map files, I've made sure that my x-coordinate in both instances of map, my x-coordinate lives at 0. So 0 in plan view along the x-axis left to right, and 0 in section view along the x-axis left to right. Both have a value of 0 where we see the stage lip. Okay, we want to cover today's audience plane. Let's attempt at doing it with a line array consisting of Lena elements from the Leo family. And we want to cover from the first row, which we call vertical bottom, as we saw in the previous webinar about autosplay. We want to cover from vertical bottom, which is the start of coverage, to vertical top, which is the end of coverage. And we want to do so in a way that makes sense. Okay. So without further ado, let's change to map, and I'm going to show you the section view first. I'm going to show you the section view first. There we go. Here's the section view. So as we saw before in the presentation, on the left-hand side is my 1 meter tall stage, and on the right side is my elevated audience plane. At the same time, I also have a second instant running, which is my plan view. This is the situation seen from above. Over here on the left-hand side, we have the stage. Over here, there is an egress area. And over here, where we have the red line, is the first line of the audience plane, and it runs all the way to the right. So let's try attempt at covering this audience plane with a center array consisting of Lena elements, which means that I'm going to go back to section view. I'm going to go back to section view, and I'm going to unhide the layer where I already prepared the Lena elements. So somebody determined that the Lena elements have to live over here in space, and now I want to cover that audience plane from vertical bottom, the start of coverage, all the way to vertical top. I'm going to use the approach that we discussed during the autosplay webinar, which you can watch on the Meyer YouTube channel, which means that first I have to select my audience plane, right-click, I go to the properties of the audience plane, and I assign I activate it as a listener plane. I want to use this line segment as a listener plane. Apply and close. All that's left to do now is select both the array and the listener plane at once, right click, and then we have a dialog which is called auto splay and overshoot adjustment. Okay, so I'm going to click on auto splay and overshoot adjustment. The dialog pops up that we discussed briefly. I want to overshoot with one whole speaker. The smallest angle that I'm willing to use today is going to be 1 degree. The largest angle is predetermined by the rigging hardware. It's going to be 11 degrees today. I'm going to press auto splay, and that gives us the following solution. Let's see how that looks by pressing predict and observing a 4 kilohertz frequency. That is to say, a 1 octave wide interval centered at 4 kilohertz, and I'm as happy as a clam in high tide. So in cross section or section view, this looks very promising. If we designate this color 0 decibels, because we can, as we go up the audience, I lose 3 decibels at the following color transition. And by the time we make it to the last row, I barely see the next color of green, and we lose another 3 decibels. And the entire audience plane is covered front to back within 6 decibels or less, which is the very thing that I was aiming for. So in section view, we are getting there. What about plan view? Let's hide this for now and go to our other instance of map and observe the section view. Okay, apologies, observe the plan view. So I'm gonna unhide our single Lena element in plan view, and there it is. There's that single speaker observed from above. If we're gonna look at the same frequency, which will be 1 octave centered at 4 kilohertz, this is the picture in plan view. And if I look at this, knowing that the first row lives over here, it looks like we're killing the people in the first row. I mean, just look at that color. If we judge a book by its cover, this would suggest that we're looking at this color, whereas in the back of the audience, we're looking at that color, and that is about 1, 2, 3, 4, 5 divisions of 3 decibels. That's about 15 decibels of difference in level. But looks are deceiving, because remember, we're working in 2 dimensions. We're working in 2 instances of map, a plan view and a section view. So I was thinking how I can make you appreciate that better. And for that, let's go to SketchUp, where we have the actual model that I've been using as a base reference for the work that we're currently doing in these 2 instances of map. So where does our section view live without its prediction? Well, this is where the section view lives. This is what we're seeing in map in section view. But of course, we also have a plan view, and without prediction, that plan view lives over here, okay? This is what our situation looks like in the plan view instance of map. So this is what we see from above, which is the picture that we have over here. Whereas if we go to the side, if we orbit to the side, then this is what we see in section view. And in section view, we have this picture without prediction. And in fact, why don't we blend in the prediction? Why don't I exchange section without prediction for section with prediction? And why don't I exchange plan view without prediction for plan view with prediction? And that gives us a completely different picture, as we're about to see. In plan view, it still looks like we're killing the people in the first row. But if we go to the side, then we see that we're not, we couldn't have been further from the truth, because in section view, it is very clear that we're not killing these people in the first row. We already knew that from looking at section view in map. So what is going on? What is going on? Where does the ambiguity come from? Let's go to our section view. Let's go to our section view, and let's go to a different layer where I've isolated the loudspeakers. So let's go to this layer that we have over here. Let me see. There's one guy in here that I don't need. Nope. Okay. So hang on with me. So let's go to layer management. I don't want you. Okay. So there we go. I only want to see the array, which is the individual loudspeakers. I don't want to see you. Okay. So let me hide this guy for now and go to the layer that I prepared. Okay, so this guy should not be there. I'm gonna put you in the original layer. There we go. I'm gonna hide you. Okay, there we go. So I managed to kill a loudspeaker. So here's what I propose. I'm going to relaunch this project. Apologies for the inconvenience. Okay, let's try that again. So I want to see you, and I want to see you, and I want to see you. Okay, so there we have our array. Notice that the second to last loudspeaker is magenta. The loudspeaker that I'm now showing and hiding, that loudspeaker has a propagation plane which runs level. What do I mean by level? This runs level. That's the propagation plane. That's the plane where the sound propagates in the vertical and in the horizontal. This is the only loudspeaker that runs parallel to what we call the drawing plane. So the drawing plane could either be the ceiling or it could be the floor for that matter, but the only loudspeaker in section view that runs parallel to the drawing plane in plan view is loudspeaker number 2 from the top. So whenever we look at a line array from above in plan view, whenever we have a picture like this, then we're basically looking at that magenta loudspeaker. That magenta loudspeaker has a propagation plane that runs parallel to the drawing plane. And by drawing plane, I mean the very plane that we're seeing right now in front of us. However, that loudspeaker does not touch down in the first row. That loudspeaker in plan view, when we observe it in section view, that loudspeaker touches down at the last row. So we're not killing the people in the first row, even though plan view suggests that we are killing the people in the first row. Because the loudspeaker that is actually pointing at the first row is the bottom loudspeaker. But that bottom loudspeaker currently runs a diagonal. And I cannot see that propagation plane, which currently runs diagonal, I cannot see that propagation plane in plan view undistorted, because the loudspeaker that I see in plan view undistorted, that is to say, the loudspeaker that I see to scale is loudspeaker number 2 from the top, the one whose propagation plane runs level, runs parallel to the drawing plane. So now we need to come up with a solution to still understand what is going on and to see whether we have enough coverage in that first row, which I cannot determine in plan view. And in order to do that, we're going to use an approach which is called Downtilt Translation. And there's 2 ways that we're going to do it. I'm going to show you both ways. I'm going to hide these layers. I'm going to show you the first way how to do it, which is I'm going to hide these layers. I go back to my original array. This is the original array, and there's the option to select that array and explode it into individual loudspeakers. If we right-click after we selected the array, then over here, there's the option to convert to individual loudspeakers. That will essentially explode the array and turn it into individual loudspeakers that I can select individually. I can rotate them individually, I can reposition them individually, and so on and so forth. I've already prepared that. So let's go to the layer management. Let's go to the file that I already prepared. Here we see those individual loudspeakers. And I'm going to select the bottom loudspeaker. And now I go to the rotate tool. And by default, the rotate tool will put the pivot point at the center of rotation during measurement, which is the point in space where the loudspeaker lived on the turntable as we obtained the polar plots. However, as we saw in the auto splay webinar, I can put the center of rotation anywhere I want, including at the point where that bottom loudspeaker enters the audience. And what that allows me to do is now orbit that point with the loudspeaker. So I can now orbit that first row with the loudspeaker. And here's what I'm going to do. I'm going to put the propagation plane of that bottom loudspeaker, parallel to the drawing plane. So this is where the loudspeaker should live if I want to have its propagation plane, which is this line, parallel to the drawing plane. This position from where it was in space to where it currently lives in space, that is the downtilt translated position. And I'm going to use this position, it's a proxy, I'm going to use this position in plan view to tell me, do I actually have the required coverage in the first row? I see that somebody rose his hand. Maybe that's been there for some while. Apologies. I see that Adam Wells wants to ask a question. Go for Adam. Okay, Adam has been commenting in the chat. He says, quick question, how do we view one array in plan view from above in map? And the question has been answered and solved on the chat. So I'm going to lower Adam's hand and let's continue with the webinar. So using the rotation tool, I've been orbiting the loudspeaker. I peeled it from the bottom of the array, so to speak, and I put its propagation plane parallel to the drawing plane. If we now go back and take note of the XY coordinates of this loudspeaker, okay, I can click on its properties and it shows me the XY coordinates of its translated position. And by that I mean where it currently lives in section view is reflected over here by the XY coordinates of the translated position. This is not where it will live upon commissioning the sound system, but this is the way to discover whether we have sufficient coverage. So I take note of those values, I memorize those, I write them down, and now I go to section view. In section view, I've already prepared this. I've inserted another Lena loudspeaker. Sorry, I've inserted another Lena loudspeaker. So I go to my layers. I'm going to reveal that layer, which I already prepared. This is the translated position in the plan view. So the real array, the physical array, will live over here in space, where we also see it in section view. However, as we learned from section view, the downtilt translated position of the bottom loudspeaker, which does the diagonal, in plan view lives over there as a proxy. And what it allows us to do is that now the propagation plane of the loudspeaker runs level to the drawing plane. And now I can click on that loudspeaker and find out, do we have sufficient coverage? Do we have sufficient coverage in the first row? So there we go. And the answer is, oops, that bottom speaker does not give us sufficient horizontal coverage in the first row. Let me try to demonstrate that. If we call this point where we see this contour, if we call that 0, because we can, okay, then I start counting colors. Okay, let's call that 0 decibels, just as a placeholder. If we call that 0 decibels, and I now start counting colors, then this is 0 decibels, this is -3 decibels, and this is -6 decibels. And within a blink of an eye, it is readily apparent that we are not covering this portion of the audience with that bottom speaker, and neither are we covering this portion of the audience with that bottom speaker. And by using the downtilt translation method, I was able to figure that out, even though we're working in plan view and in section view. So I want to elaborate a little bit on this. I would like to elaborate a little bit on this because what is the other way that we can draw the same conclusion? Let's go back to section view. And this time around, I'm going to show you another approach. There is no preferred method, I'm going to reattach our loudspeaker to where it used to live, which is at the bottom of the array, which is over there. That is, of course, where we deploy the loudspeaker in space. And now I'm going to use a different attempt. I go to the architectural 8, and I'm going to draw a line segment starting at where the loudspeaker touches down on the first row. There's my line segment, and I'm going to put the line segment, I'm going to put the line speaker, connect the speaker to the first row. So there's my line segment. I'm now going to select the line segment, which is the distance between the loudspeaker and vertical bottom where coverage is supposed to start. I'm going to select the rotate tool. By default, the rotate tool puts the center of rotation in the middle of the line segment, but remember, I'm free to put the pivot point anywhere I want. This time I'm going to put the pivot point once more at where that line segment enters the, starts in the audience. And again, I can now rotate this line segment as the dial of a clock. And I'm going to make it level like I did before without actually pivoting or orbiting the loudspeaker, but it still gives me a measure of distance, which is what it's all about. Okay, so let's select this line segment. Let's click Edit Properties, which brings up a dialog. And now we can see that if we look at our polar coordinates, okay, we can make absolutely sure that that line segment is level, but it also shows me the length of that line segment, which is of course the same distance as we saw before, which is roughly 6 meters. It also gives me once more, if I press Cartesian coordinates, it gives me the location of where that translated position would have to live in space, as we saw before when I peeled off that bottom loudspeaker. So there's two ways how you can come up with these x coordinates. It's the x coordinate, which is mission critical, because I want to copy that x coordinate into my plan view. Because if we go to our loudspeaker in plan view, hopefully everyone is able to appreciate that the x coordinate of the translated position is functionally the same x coordinate as the x coordinate of the loudspeaker in section view. But there's even an easier way. Wouldn't it be great if we can somehow predict what the usable width will be of this loudspeaker, the bottom loudspeaker of our array? If we could somehow predict that over here we run out of gas, and if we go in the other direction, we run out of gas. And we can do that. And for that, I will go back to the PowerPoint presentation. Okay, so here we see that same loudspeaker in its translated position, which we derived in the way that we just discussed. If we call that color 0 decibels, which we did, this is the same picture as before. The only thing that I did to save real estate in the PowerPoint presentation is that I rotated the entire plan view by 90 degrees. But other than that, it is the same, it's the same prediction, it's the same plan view. And again, we have confirmation that if we go 2 colors to the right, that we lose 6 decibels. If we go 2 colors to the left, we lose 6 decibels. And that tells me that I have a local problem over here and I have a local problem over there. Wouldn't it be convenient if we can somehow predict that usable width? Now, what do I mean by usable width? By usable width, I mean the width between the -6 dB points. And the answer is yes, we can predict this using the so-called triangle. Because notice that we're dealing with a triangle. Our loudspeaker lives over here. One -6 dB point lives over here. The other -6 dB point lives over there. And this is a triangle. And it has a base, which has a certain width, the very thing that we want to know. And of course, it has a height from the base of the triangle to the tip of the triangle where the loudspeaker lives. And I know these dimensions in practice. We just doctored that out using the translated position. So wouldn't it be cool if we can somehow predict the width of the base of that triangle as a function of the height of the triangle or the distance between the first row and the loudspeaker? And for that, there is a very straightforward equation which tells us that the width of that base between the minus 6 dB point is equal to the height of that triangle times a certain multiplier. And those multipliers you will find over here for various Leo family products. So Leo family products in the horizontal are constant Q devices. We talked at great length about that in the previous webinar. And Leo M, according to the data sheet, is 75 degrees. Line M is 90 degrees. Lena is 100 degrees. And line W is 110 degrees. The line WXT is 110 degrees. And the leopard is 110 degrees. And in the third column, you see the multiplier that you need to use for those particular products. So what does it mean? Let's take the Lena example that we're using in today's webinar. For whatever reason, it has a multiplier of 1.5, which tells me that if we live at a distance of 10 meters to the loudspeaker, then the height of my triangle is 10 meters. It also informs me that the width, which is the very thing that we're trying to figure out, that the base of the triangle has a width of 10 times, which is the distance, times the multiplier of that particular loudspeaker, which is 1.5. I use a comma. Some people use a decimal point. I use a comma. Tells me that the width of the base is going to be 15 meters. 7.5 meters I can move in this direction, and the other 7.5 meters I can move in the other direction. And I can use that to inform me what the available width will be at a given distance to the loudspeaker based on the coverage angle of that loudspeaker. So if you want to make a screenshot of that table for Meyer sound loudspeakers, now would be the time to do it. Okay, so to help you visualize that, what is going on, what is going on, let's go back to the SketchUp file, because I have prepared these triangles. And this is the loudspeaker that lives in the bottom. And if we now orbit the map, if we now orbit the SketchUp file, you can see that that bottom speaker will be a couple of seats short on either end. It does not have sufficient width to reach those seats, and it doesn't have sufficient width to reach those other seats. Okay, so what about the second speaker from the bottom? What about the second speaker from the bottom? Let me mute some microphones. Okay, all of them are muted. So what we ended up doing is, let me zoom in to give you a better understanding of what it is that we're doing. Okay, we multiplied the distance from the loudspeaker to the first row. This distance is something that you are expected to know in practice. We multiplied that distance by whatever multiplier is required for the loudspeaker du jour. Today it's a Lena, which is a multiplier of 1.5. And that tells me that if I multiply this distance that we have over here, if I multiply this distance by 1.5, it will give me the available width in that first row. Let me take the cross section out of the way so that you can see the triangle in its full glory. There we go. So by multiplying this distance by 1.5 for Lena, it will tell you that this is the available width, the very thing that I wanted to know. So what about those other loudspeakers? Let's go back to section without the prediction. Of course, by now, you probably suspect that as the distance between the loudspeakers and the audience increases, which it does over distance, if that distance increases, then surely if we multiply those distances with the multiplier of whatever loudspeaker that we're using, that the width also gains market share. So let me blend in the other triangles as well. This is the second to last speaker from the bottom. Let's blend in the next loudspeaker. This is the third to last, fourth to last, fifth to last, so on and so forth. So by doing this, I suddenly get a very good grasp of where I have underlap and where I have overlap. Because by using this technique, I can see in a blink of an eye that we have an area over here which is underexposed and probably needs an infill. It's a minority of the audience that needs a local solution. And of course, the same is true at the other side. Over here, because it's a symmetrical exercise, we have a similar area that is underexposed, nothing that an infill would not be able to address. So by using this technique by Bob McCarthy, okay, we can very clearly see where the edge of coverage runs, even though we started working in 2 dimensions. Okay, so let me give you a little bit of a bird's eye perspective. Over here, you see all those triangles, okay, and it's clear to me that we have too little coverage in the front, therefore we have too much coverage in the back. We divided the error, the majority of the audience is covered, and that basically eliminates the need to resort to downtilt translation altogether by simply using the technique that we see over here. So these are the values for Leo products, Leo family products, which only leaves one more question to address. What about an omnidirectional source? Because for reasons that we discussed during the previous webinar, even line array elements at low frequencies are omnidirectional. What is the multiplier if you are omnidirectional? Well, if you're omnidirectional, you have 360 degrees of coverage and the multiplier is roughly 3.5. Let's see if we can validate that in the plan view of map. That section view, apologies, I did not intend to go there. Let me hide this temporarily and let's go to the plan view. Mind you, we're still looking at the translated position. This is the real position where the loudspeaker lives. This is the translated position of that bottom loudspeaker. And to help you see what we're talking about, I've already prepared that triangle. Okay, this is exactly the same story that we've been looking at so far. Apologies, one loudspeaker at a time. It's the same story that we've been looking at so far. It tells the same story. This is a triangle in the custody of the constant directivity horn high frequency section in the horizontal plane. Line array elements by Meyer sound are constant Q devices in the horizontal plane. So in 4 kilohertz, 2 kilohertz, 8 kilohertz, this is consistent. But a Lena element, like all line array elements, ultimately, if you go low enough, becomes omnidirectional. And this is 1 octave at 63 hertz, centered at 63 hertz. And if we now start drawing a triangle, okay, starting at the source, if we call this color 0 decibels, then this is -3 decibels, and -6 decibels is somewhere outside the drawing plane. So the width, if you will, at 63 hertz is much wider than the width in the custody of the horn. And if I blend in that triangle, of which I can determine the width by multiplying this dimension multiplying that dimension by the multiplier for an omnidirectional source, which we have over here. The omnidirectional source is a multiplier of 3.5, then I get a different triangle. And let me reveal that triangle as well. Here we go. This is the triangle at 63 hertz. And needless to say that that triangle has a base which is much wider than the triangle that we saw for frequencies at 4 kilohertz, which is this triangle. I can also show you that in SketchUp before we're going to finish today's webinar, but it's safe to say that if you live over here as an audience member, or you live over here as an audience member, where you're staring into the high frequency section of that bottom loudspeaker, that the only thing that will not be missing over there are going to be low frequencies. It's everything else that's missing over there, which are your fresh and intelligible mid and high frequencies. And I can also make you appreciate this in SketchUp, because in SketchUp, I have prepared that bottom triangle at 63 hertz, which looks like this. So the bigger triangle gives you the width at 63 hertz, whereas the smaller triangle gives you the width at 4 kilohertz, 2 kilohertz, 8 kilohertz. And again, it is readily apparent that the only thing that will not be missing over here are low frequencies. They're there, but it's everything else that is missing over there, which are fresh and intelligible mid and high frequencies. And using this approach, you can visualize this very, very, very quickly. So that leaves you with several options to still design a proper system taking 3 dimensions into account, even when designing in 2 dimensions, which is what we typically do in a map ecosystem, because the technique that we just showed will still allow you to predict the performance in 3 dimensions to a high degree of accuracy. So that is downtilt translation. Let me make sure that we discussed all topics. Today, we learned how to run multiple instances of map_xt at once. In an Apple ecosystem, you have to duplicate the application several times. Working in multiple dimensions can also be done. Downtilt translation, how do I put the propagation plane parallel to the drawing plane? That is the downtilt translation process. And finally, there is a solution that allows you to actually predict the usable width between the -6 dB points, which is the approach that we discussed over here. And that basically eliminates the need for downtilt translation altogether. Everything that we've discussed so far can also be found at the Meyer Sound website. If we go to the Meyer Sound website and we go to the video section, then we're taken to a new page, and on that page, there's several topics. If we go to map_xt, then you will see that the second chapter in map_xt is the video about downtilt translation, and it explains exactly the same things that we discussed just now. This webinar will be uploaded to youtube.com/thinking_sound, which is Meyer Sound's YouTube channel. So expect to find it there. Within the course of the day, if not tomorrow. And the next webinar will take place on Friday, April 3rd, where we will discuss the preparation of CAD files and how to import them into map_xt. That concludes the official part. I'm gonna stop sharing for now, and let's go back to the camera. And then we have a couple of minutes left where I can address questions. So I see that David Muddyman has rose his hand. Go over, David.
Hey, can you hear me?
Yes, I can, sir.
Oh, that's great. That really works. The translation numbers for some of the narrower boxes, for example, UPA2P and MSL4, what would those numbers be?
Well, let's see if there's a way to make those numbers available in the comments of the video. How does that sound?
That would be great.
Okay.
That'd be fine. Thank you.
Thank you, David. Any other questions at this point? Okay. Well, if you guys have no more questions, then this concludes today's webinar. Thank you for participating, and we hope to see you on Friday. Okie dokie. Bye-bye.